One? Yeah. Okay, good. Okay, a couple of announcements. One, the schedule's changed today. First, the organizers have given me a little bit of extra time so that I won't rush, really rush. So everything's pushed back a little bit, and sound talk will have an extension bit that he estimates to 30 minutes. And I know the organizers have stressed, but I'll just remind you also, the banquet is not at the hotel where most of us are staying. It's an equal distance the other direction at the Marriott. So I'll see everyone there at 6. The other thing is just sort of a semi-personal announcement. The 10 people who are in the project group with Michelle and Rafe and me, I'd like to have a meeting here in this room just to talk about logistics a little bit, maybe for 10 or 15 minutes after the last talk, so after Sounds finishes his talk. Maybe we'll just kind of congregate in the corner here or something, okay? So I would like everyone in my group to be at, the 10 official group members to be at that. Good. Okay, so today what I want to talk about is integral points in orbits. And as usual, I'll stick to working over Q. So the first natural question, you take a rational map, and you take a rational starting point. And I mentioned this in the first lecture as a natural question. Can this set of integer points in this orbit be infinite? And the obvious answer is yes. There's trivial cases. For example, if you take a polynomial, so yes. If you take a polynomial with integer coefficients and you start with an integer, then the entire orbit is integers. And there are some other examples. For example, well, the easiest next example is like 1 over z squared, or 1 over z to the d, an alpha member of z. Then every other entry in the orbit will be an integer. Right, you'll get alpha, then the second entry will be alpha to the fourth entry will be alpha to the 16th, and so on. And more generally, the same would be true if any iterate of phi is a polynomial. But as I think I mentioned in my first lecture, that doesn't actually happen for higher iterates. So there's this proposition, which is has nothing to do with number theory. If you take a rational function, always degree at least 2, and if some iterate of C is a polynomial, then already the second iterate is a polynomial. And the proof, which is not too hard, as I mentioned in that first lecture, is it uses Riemann-Hurwitz. Basically to show that this map has to have a fixed point that's totally ramified, and then that'll show it's a polynomial, well, at infinity. Okay. So in view of that proposition, one can't expect much more than something like the following theorem. So take a rational map of degree at least 2. Let alpha be the starting point. And assume that the second iterate is not a polynomial, which implies no iterate is a polynomial. Then, in fact, the orbit has finitely many integer points. Okay? And the proof, which is what I want to sketch for you today, is an adaptation with some added complications of one of Ziegel's proofs that affine curves of genus at least one have finitely many integer points. So this is sort of a dynamical analog of that theorem. Okay. But actually, I'm going to prove something a bit stronger. With the same assumptions. And let me assume that, for the second thing, I'm going to assume that alpha is actually a wandering point, okay? If alpha is pre-periodic, the first theorem is rather easy to prove because the orbit's finite, okay? So assume that alpha is wandering. And write the nth iterate of alpha as, say, an over bn as a fraction in lowest terms. Okay. So what the first theorem says is that there are only finitely many n's for which b sub n is 1, for which you get an integer, right? A much stronger result is that, in fact, b sub n is always at least almost as large as a sub n. Okay. Then the lim inf as n goes to infinity, here's one way to do it. The log of bn, so you can think of that as kind of the number of digits in bn divided by the number of digits in an. That never gets much less than 1, and so the lim inf is actually 1. So roughly speaking, the denominator, if you take n big enough, the denominator has about as many digits as the numerator. So in particular, it can't even be close to being an integer. Okay, and it's this theorem that I want to sketch the proof for you. All right, so what we want to prove is that as n gets large enough, log bn is about the same size as log an. So let me suppose to the contrary, this isn't true. We'll end up with a contradiction. So suppose instead that, that the a sub n is actually significantly bigger than the b sub n. Okay? And the way I'm going to write it, or to say it another, the b sub n is significantly smaller than the a sub n. So let's suppose that b sub n is smaller than a sub n to the 1 minus epsilon for a whole sequence of n's, going to infinity, where I've fixed some epsilon for some fixed epsilon greater than 0. And there are probably going to be some points in the proof where I don't want epsilon big, so maybe I'll say epsilon is between 1/2 and 1. And 1/2 and 0. Okay? So this would contradict the statement of the theorem. Well, one thing that we'll need to know is that, I'm basically trying to prove that b sub n gets big. Well, to start with, I want to know that at least one of a sub n and b sub n gets big. But that comes out from our height estimates. Okay? So let me see. So I can rewrite this inequality here. Yeah. So let's do it this way. The a sub n over b sub n is greater than or equal to a sub n to the epsilon. Well, I should put absolute value signs, right? That's just rewriting this inequality. A sub n over b sub n, of course, is just the size of phi to the n of alpha, because a sub n over b sub n is phi to the n of alpha. That's the definition. From this inequality, it's clear that a sub n is bigger than b sub n in particular, right? We're saying it's significantly bigger. So a sub n is actually the larger of a sub n and b sub n. So this this is simply the maximum of an and bn to the epsilon. But the maximum of an and bn is just the height of the rational number an over bn. Okay? So this is just the height of an over bn. The epsilon, which is the height of phi to the n of alpha to the epsilon. And it's convenient to use the exponential height instead of the multiplicative height here. So let me just write this, run out of space, as e to the logarithmic height of phi to the n of alpha. No, epsilon logarithmic height. Okay. So that's just rewriting it using logarithms. And remember, the ordinary height looks like the canonical height up to a bounded difference, right? So this looks like e to the epsilon, the canonical height of phi to the n of alpha, plus O of 1. I'll absorb the epsilon into the O of 1, because really all the constants are allowed to depend on everything in sight except for n. It's just the n dependence that we're trying to keep track of, okay? All right, well, why do this? Well, obviously because the canonical height behaves nicely when you apply it to a point that the function's been applied to, right? So the canonical height of phi to the n of alpha is just d to the n times the height of the point. So epsilon d to the n, the canonical height of alpha, plus O of 1. What I'm trying to do here is say that the absolute value of phi to the n of alpha gets really big. And you can see this function's growing very rapidly with n, provided what? Provided this canonical height's not 0. And that's where we use the fact that alpha is a wandering point, which I proved for you is equivalent to the canonical height being positive. So this is strictly positive, and of course independent of n, because alpha is a wandering point. So we're going to need this inequality later. So, am I too low? Too low? There. Oops, a little further. And is it focused? Yeah, that's better. Okay. Actually, yeah, so I'm actually going to keep track of the epsilon here also. But what this is saying is that phi to the n of alpha is greater than or equal to some constant raised to the epsilon d to the n power for some c that's strictly bigger than 1. Actually, there's going to be a ton of constants floating around, and rather than call all of them c when they're different, I'll try to number them consecutively. But okay, where c1 and in general, the c sub i's are allowed to depend on alpha and on phi. Okay. Actually, yeah. C1's not going to depend on epsilon either. I should probably write this as C1 times C2. Yeah, C1, C2. Where C1 only depends on alpha and phi. C2 is allowed to depend on epsilon also. Okay. But the thing to take away from this is simply that the size of phi to the n of alpha is growing, sort of doubly exponentially in n. Well, what does that mean dynamically? It means that phi to the n of alpha, as n grows, is getting close to infinity. I mean, it's going to infinity very rapidly, right? So in particular, phi to the n of alpha gets close to infinity. And this is much more precise, of course. It tells you how fast it's getting close. Good. So here's the rough idea on the proof. Phi to the n of alpha is close to infinity. So I'm gonna fix some k, which we'll see how to choose later. The important thing is k will be independent of n. Okay. Well, if phi to the n of alpha is close to infinity, then phi to the n minus k of alpha is close to some point gamma in the kth inverse image of infinity. Okay. Remember I said k is going to be fixed independent of n. So up to finitely many choices, I'll just have a gamma here, and I have this whole sequence of rational numbers that are going to be real close to this irrational number. And that should bring to mind Roth's theorem. So what we're going to do is get a contradiction to Roth's theorem. Okay, that's the rough idea. Okay, well, what do we mean? What do I mean that phi to the n is close to infinity? Remember, we're using this chordal metric on P1 of C. P1 of C topologically is just the unit sphere, and point infinity is kind of up at the top. Okay, so the biggest distance between 2 points is 2, and a neighborhood of infinity looks like a neighborhood of any other point. So if P is close, actually I don't want to use P. If some gamma is close to infinity, then the distance from gamma to infinity, if you just do a little geometry or look at the formula that's in the notes, but I didn't put on the board. I think actually Rob put a version of the chordal metric. If you just look at it, basically this will be more or less like 1 over the absolute value of gamma, which is reasonable. As gamma gets big, you're getting close to infinity, the distance goes to 0. Okay. So explicitly, from this estimate, what we get is that the distance from phi to the n of alpha to the point at infinity, I'm going to drop the c in front, looks more or less like a constant to the epsilon d to the n. So as n increases, it's getting very, very close to infinity very quickly. Okay. And now I want to say, well, in that case, if I, instead of applying phi n times, I only apply n minus k times, I'm not quite as far, but I kind of take the inverse image of both these points. And the inverse images should still be close, more or less. Okay, so I want to do this computation first under an additional assumption. I keep doing this. That's good. Okay, so we're going to make the following assumption, which will simplify the calculation, okay? Let's assume phi has no critical points. Okay, or another way to say it, it's everywhere unramified. Okay. Now, hopefully, as I'm looking out, I see some dubious expressions on your face, okay? Because if we make this assumption, I mean, the proof I show you is going to be completely valid, but how many maps will it apply to? Not very many, thank you. Yeah, none, right? It's the empty set. Because the Hurwitz genus formula says 2D minus 2 is the sum of the ramification indices minus 1. So this side's positive, so there's got to be at least some ramified points. In fact, you always have to have at least 2 ramification points, okay? So we're going to prove a theorem about the empty set of maps. But then I'll go back and show you how to fix it. And it's very illuminating because fixing it shows you exactly where the assumption that phi is not a polynomial comes in. Okay. All right. Under this assumption, I mean, if a map's unramified, then essentially it preserves distances up to bounded amounts. Okay. So unramified implies roughly that the distance between phi of x and phi of y is approximately the distance between x and y. Okay. Again, for the purposes of the lecture, I'm leaving out plus O of ones and things. I mean, you can fill this in if you want to make it rigorous, but this is what's really going on. Okay. So in particular, the distance from phi to the n minus k of alpha and beta. Yeah, so what I'm going to do is I'm going to let beta be in the inverse image of infinity, and I'll take it to be the point in this finite set of points that's closest to phi to the n minus k of alpha. Okay? Then this distance will be approximately the distance from phi to the n of alpha to phi to the k of beta. See, I'm just applying phi k times to both this, so I'm using this line k times. Admittedly, this constant here will depend on k, but as I said, k is going to be chosen independent of n. And this is crucial. At the end, we have to be very careful that k doesn't depend on n. Well, phi to the k of beta is infinity, because I chose beta to be in the kth inverse image of infinity. And we know that this distance is very small, right? That was, that's over here. This is more or less constant to the epsilon d to the n. So remember, we have this sequence of n's, n1, n2, n3. You'll actually have to split it up into a subsequence, sort of one for each point in this finite set, and we choose the one that works best. And I'll ignore that also. We have this sequence of n's, so that these distances are getting really small. But if you have points just in the affine plane, these points won't. Actually, there's an extra argument if beta is actually infinity. I'll ignore that too. So beta will be in the finite plane somewhere. If you just have 2 points in the finite plane and kind of keep them away from infinity, which you can do, then the distance between 2 complex numbers is just the absolute value of their difference. So what we roughly get is phi to the n minus k of alpha minus beta. It's like approximately 1 over c to the epsilon d to the n. So I have this fixed algebraic number, this sequence of rational numbers, and the rational numbers are getting really, really close to the algebraic number. Couldn't beta be a rational number as well? Well, actually, that's a good point. In principle, yes, and it's easy enough to deal with that case, because if you have a rational number, it actually only has one good rational approximation itself. You can use that. But a fancier thing to do is, if k is big enough, well, there's essentially no rational numbers here because the heights are going down. So you have to be in an extension field. Unless there's a periodic rational point there. And then actually, yeah, you're right. You would have to deal with it separately. Okay, yeah. All right. What does Roth's theorem actually say? It says that it says if you're if a rational number is really close to an algebraic number, that can't happen. How do you measure the closeness? You measure the closeness in terms of how big the numerator and the denominator of your rational number are. And that kind of determines sort of how big a denominator here you can get. So we have to compare the numerator and denominator here, or say the denominator here, to the size of the denominator there. All right, that's a little vague. Let me actually do the calculation. Starting from the very beginning and working it through to where we get a contradiction. Okay? So I'm going to start with 1 over an to the epsilon. Remember, phi to the n of alpha is a sub n over b sub n. So this is just the numerator. And our assumption on this sequence of n's, if you go back a couple slides, was that this is greater than or equal to an over bn. Well, bn over an. And if you just rearrange this, it basically says that the a sub n is significantly bigger than the b sub n. Or even just staring at it, you can see that, right? It says this fraction is small. So the a sub n is significantly bigger than the b sub n. That's the assumption that we're trying to show is false. All right. B sub n over a sub n is actually just 1 over phi to the n of alpha. That was the definition of phi to the n of alpha is a n over bn. So that's easy enough. And this is a very small number. And as I indicated before, it essentially tells you how far phi to the n of alpha is from infinity. Okay? This is essentially the distance using the chordal metric from phi to the n of alpha to infinity. And this is all elementary calculations. Okay. All right. Now remember, I chose this beta in phi to the minus k of infinity that was close to phi to the minus nk. All right, so let me just write this as the distance from phi to the n of alpha to phi to the k of beta, because beta is in the kth inverse image. And I chose the right beta so that it's the one that's closest to phi to the n minus k of alpha. So this is approximately, and again, I'm just copying something from a previous slide. What I'm doing in this step is I'm applying phi inverse k times. So this step is the one that uses the assumption, assuming phi is unramified, has no critical points. Okay? So that's the step that's completely bogus, but we'll use it anyway. Okay. Well, now these 2 points, up to dealing with some special cases, are just 2 complex numbers. And the distance between 2 complex numbers is essentially their difference, well, the magnitude of their difference. So that's easy enough. And now I'm thinking of n ranging over this sequence. N is n1, n2, n3, n4, and so on. Okay? So I have a whole sequence of points here, rational numbers. This is some fixed algebraic number. So Roth's theorem tells me that this is greater than or equal to some constant. I'll just use this notation. This says it's bigger than some constant. Divided by, well, essentially the denominator. So I'll put something even bigger than the denominator down here. The height of phi to the n minus k of alpha. Well, no, not quite. To the 2 plus epsilon. Right? And then my constant would depend on epsilon. But I'm using epsilon for something else. And I don't really need it quite that precisely. Why don't we put a 3 here? So I'm using Roth's theorem with exponent 3. Just to pick some. You put 2.5 there, you put 17 there, it doesn't matter. Just your favorite fixed number. So this is Roth's theorem. Okay. So this step up here was bogus. This step here is a very nice theorem, but it's using a very deep result. And it's also, Roth's theorem is ineffective, so this makes the whole proof ineffective too. But one must make sacrifices somewhere. Well, now I just want to estimate how big the height of phi to the n minus k of alpha is. But again, I can use the canonical height, estimates. So this is more or less, well, let's write it with the exponentials, more or less e raised to the 3 times the canonical height of phi to the n minus k of alpha, plus 1, which I'll ignore. The canonical height, when you apply phi and n minus k times, gives you what? Gives you a d to the n minus k. So this is, I'm sorry, minus, thank you. Yeah. Oh, we get a really nice inequality if we didn't have the minus there, wouldn't we? Because that's in the lower bound. Yeah, okay, thanks. So we get e to the minus 3, d to the n minus k, canonical height of alpha, plus no of 1. Right? Okay. And again, taking the canonical height and moving it back to the ordinary height. What this will more or less be is, well, you'll get, you'll get the multiplicative canonical height, so e to the h hat of alpha. I just want to use the fact that this is strictly positive, okay? So rather than writing that, what we'll get is a constant here that's independent of n, raised to the d to the n minus k. Oh no, I do not want to do that. I'm sorry. Let's just toss that slide. Let me just do a side calculation here because I don't want to fill it up there. 1 over e to the canonical height of alpha, just kind of, I mean, we have that raised to some power, is essentially 1 over e to the ordinary height of alpha up to, a constant, which is the multiplicative height of alpha, which is the height, I'm sorry? Yeah. I'm sorry, no, okay. Let's go back. There's always one point in the proof thing. What I want to do is pull out the d to the n minus k. This last line, I pulled out the d to the n minus k. I actually just want to pull out a d to the minus k. And write and put phi to the n of alpha here. And I assume that this is now unreadable. So let me recopy the left-hand thing I started with and rewrite this last line, okay? I get this is bigger than e to the minus, 3, d to the minus k times the canonical height of phi to the n of alpha. Because when you apply phi, the canonical height gets multiplied by d. So essentially if you apply phi inverse, it gets divided by d. Okay. And e to the canonical height is more or less just the ordinary height. So this is essentially the ordinary height of phi to the n of alpha to the minus 3 d to the minus k. Right? Yes. Excellent. But phi to the n of alpha is just a n over bn, right? So this is just the maximum of an and bn to the 3 to the d to the minus k. But in fact, an was bigger than bn under our assumption. Remember, the numerator's bigger than the denominator. So this is just an to that power. Maybe rather than a negative exponent, I'll write it in the denominator. Okay. So now, can you see, I'll get a contradiction to there being infinitely many integers an if this exponent here is smaller than that exponent there. So if we choose k so that 3d to the minus k is significantly smaller than epsilon, for example, is less than epsilon over 2, then we get that an is bounded for all n equals 1, n1, n2, n3, which is a contradiction, because we assumed we had an infinite sequence of these rational numbers whose numerators were going faster than the denominators. Notice this, I mean, this is crucial here, that the k we choose doesn't depend on n. It just depends on the epsilon and the degree of the map, which is fine. Okay? So everyone believes the proof. The problem with this proof, of course, is that this step here isn't valid unless the map's unramified. And every map is ramified. But it does pin down at least where the potential problem is. The potential problem is essentially the way we used the fact it was unramified was that it preserved distances, more or less. But a ramified map does not preserve distances. It can significantly change them. Okay? So to actually do the proof correctly, we need to figure out what happens if phi is ramified. How does it affect distances? Okay. So, I've used gamma before, but I'll use again. Suppose that gamma is a critical point. And suppose that beta is close to gamma. How is the distance from phi beta to phi gamma related to the distance from beta to gamma? Well, in a neighborhood of gamma, phi of z will look like phi of gamma plus, now I'm just doing the Taylor series expansion. The first non-zero term in the Taylor series expansion is the one whose power is the ramification index, right, plus other terms. So if you just plug in z equals beta, you see the distance from phi of beta to phi of gamma is more or less the distance from beta to gamma raised to the ramification index power. So locally that's what happens. That locally in a neighborhood of a critical point, the distance, phi shrinks distances, and it shrinks it by a power of, given by the ramification index. Okay. So, if you now go through this proof and we get to this step here, I'm actually not applying sort of an estimate like this to the map phi. I'm applying it to the map phi to the k, right? Because I've got phi to the k here. So this very dubious step, if I want to fix it, should really read, that box there, should really read that the distance from phi to the n alpha to phi to the k of beta is approximately the distance from phi to the n minus k of alpha to beta raised to the ramification index at beta of not phi, but phi to the k. Because I'm applying this with phi to the k in place of phi. Okay. And note this approximation thing here. I mean, this kind of depends on phi and on k, but it doesn't depend on on n or alpha or beta. Well, actually, it can depend on beta also, but we're taking a particular beta here, but it's independent of n. Now, what happens if I take this and just carry this through the rest of the proof? Okay. Well, all I have to change is, I mean, every place, starting with this step here, I just have to raise everything to this power, right? So the final conclusion is almost the same. I have this exact same set of inequalities, except I needed to put the ramification index at beta of phi to the k here. Ramification index, phi to the k, so on. So this gets raised to the ramification index of phi to the k. Okay. And unfortunately, so in this box here, I have this ramification index of phi to the k here. Okay. So we'll still win. Everything is still fine. So we win if we can make this quantity here, so 3 times the ramification index of phi to the k over d to the k, small. So smaller than, I would say, epsilon over 2, by choosing some particular large k. Okay. And there's a little subtlety here that as you choose different values for k, the beta is going to change also. Okay. But there's no n's floating around. Well, what can go wrong? Well, here's something that can go wrong pretty badly. Suppose that phi of z were actually a polynomial. Okay? Well, then beta is actually going to end up being the point at infinity. And what's the ramification of a polynomial at infinity? Well, infinity is a totally ramified fixed point. So it's as ramified as possible. So the ramification index of phi will actually just be d. And if you iterate, it'll just get multiplied that. So the ramification index will actually be d to the k. And if this numerator here is d to the k, you're going to have a hard time making this small. And the same thing will happen if any iterative phi is a polynomial. Okay. So the final step in the proof is a little proposition, which I'm going to say it in words and then state it a little more precisely. If the second iterate is not a polynomial, and actually you could take, this is actually a complex, a theorem about maps over the complexes, so it doesn't have to be over Q, but so if phi squared is not a thing, then as you take iterates, phi to the k makes the ramification spread out, or maybe makes the critical points spread out. And the proof is an adaptation of the proof that if phi squared is not a polynomial, then no iterate's a polynomial. So it uses the Riemann-Hurwitz formula and kind of keeps track of stuff. So more precisely, what you get, is, suppose I take sort of any point that's in the inverse image of infinity. Okay. And I want to see how, kth inverse image. And I want to see how ramified phi to the k can get at beta. Okay? So I'll take the maximum over all these points. And I want to know how big the ramification index of phi to the k can be at beta. Okay? If you throw out this assumption, the answer is the ramification index can be d to the k. It can be as large as possible. But with this assumption, you can show that it grows slower than that. So it's like lim k goes to infinity. And in fact, one can get much more precise estimates out. In particular, if infinity is not a pre-periodic point, so if infinity is a wandering point, so just sort of a side thing, if infinity is wandering, then e sub beta phi to the k in this setup. I meant to look this up. I think what you get is 2d minus 2. In any case, you get a bound that's independent of k. Okay, so obviously this limit goes to 0. However, if infinity is almost totally ramified, then this ramification index can in fact grow with k. It just can't grow quite as fast as d to the k. Okay? And this is exactly what we need to finish the proof, right? Because what did we need to finish the proof? We needed to make this ratio smaller than epsilon. Well, this proposition says that that ratio goes to 0, so I can make it smaller than epsilon. Okay? And that essentially finishes the proof. Modulo one or two details, and obviously filling in the details of the proof of the proposition. So, yeah. Yeah, well, the way I set it up, it would have to be conjugate to a polynomial and leave infinity fixed, because we're talking about being polynomial with respect to infinity. And in that case, it would be a polynomial, I think. Z squared plus 1 z squared over z plus 1. But not by something fixing infinity, I think. The conjugation has to fix infinity, because we're talking about integrality with respect to infinity. So if you conjugate this to a polynomial, and this is a great question, by the way. If you conjugate this to a polynomial, okay, then the integral points in the orbit with respect to this polynomial will not be integral with respect to infinity for this map. They'll be integral kind of with respect to some other point, the point where infinity came from. Okay? Yeah, and it conjugates by f to a polynomial. And if you take call it polynomial c, then if c to the n of alpha is an integer, phi to the n of alpha won't be, because it'll look like f inverse c to the n of alpha f. Well, basically, I mean, you apply it to f inverse alpha, so you get something like this. So this would be an integer. But the conjugation doesn't preserve integrality because you've moved infinity. So if f inverse of it will no longer be integral. Okay, I didn't quite say that the critical points spread out. What this says is that critical points that are in the inverse image of infinity spread out. Okay? And so that theory makes critical, yeah. This is a usual problem that stating it in words wasn't quite precise. But the way the theorem is phrased, everything's kind of with respect to infinity. A general statement doesn't do that. And if you look, well, actually, no, the notes don't have it, but like in the paper where I proved this, there's a very general statement about being integral with respect to an arbitrary point, and so it's set up that way. Okay, yeah, good. Any other questions? Okay, then in the last 10 minutes, because the organizers were kind enough to give me 10 extra minutes, and actually I may only need 5 of them. I just wanted to quickly show a kind of a fun construction. We now know, all right, so I'm going to assume that phi squared is not a polynomial. So the orbit of any point has finitely many integral points. And I think this is pretty much an automatic thing to do in number theory. Anytime you have a finite set, you want to know how big it is. So how large can this be? And some of the deepest theorems in Diophantine equations actually are answering this kind of question in various settings. Like, elliptic curve has finitely many rational torsion points. Well, how many can it have? There's no more than 16. Getting the 16 is much harder than just showing that for each individual elliptic curve, it's finite. And the answer is as large as you want. Okay. So this is sort of an adaptation to dynamics, but the adaptation's trivial, of an idea that I think it's originally due to Chawla on elliptic curves. So here's how to do that. Proposition. For all n, so I'm going to fix phi. No, I'm sorry. For all n, there exists a rational map with phi squared not a polynomial, and a starting point alpha, such that alpha, phi squared alpha, up to phi to the n alpha are all integers. Okay. And here's the way to do it. Basically, take any map at all. Well, it's not whose square isn't a polynomial. And take any beta as your starting point, some wandering point. All right? And write the nth iterative beta just as an over bn. And the idea is going to be that I'm going to conjugate c in order to clear out a whole bunch of the denominators. Okay? And I just want to make sure. Okay, so let's let b b1, b2. Actually, I guess I should probably put b0 in here because I'm going to start with beta. You might want to choose beta to be an integer for simplicity, but it doesn't matter. All right, up through bn. And if you want to be a little bit more efficient, you could take the least common multiple of these instead of the product. But fine. And then just take phi to be, and I always get the conjugate on the wrong side. So I want it to be the b on the outside. So I just conjugate by b. So phi of z is b times c of z over b. and let alpha be b times, no, what are we, phi of alpha, I'm going to put alpha in here, yeah, be b times beta. All right? Then you can see that phi to the n of alpha, just because I've conjugated by z goes to z over b here, will be b times c to the n of, well, alpha over b, so it's beta. So this is just b times a n over bn, and I rigged up b so it canceled all the denominators, so I get an integer if n is less than or equal to n. Okay, so kind of a silly thing, really a cheat. And you can do the same thing on elliptic curves. If you want an elliptic curve that has 100 million integer points, you just take, well, a Weierstrass equation. You just take a Weierstrass equation with a rational point, take its first million iterates, and then make a change of coordinates to clear all the denominators. Okay, so that's kind of cheating. So instead, it would be reasonable to say, well, what about if you don't cheat? So I want to rule out cheating somehow. On elliptic curves, the way you do that is you require the Weierstrass equation to be what's called minimal. Okay, so you've kind of gotten rid of as much bad reduction as possible. So let me make a definition. Let me say that phi is minimal, except there's another notion of minimal, so I'm going to say affine minimal. If its resultant is equal, that's not a resultant. Remember, the primes dividing the resultant are the primes of bad reduction. So its resultant is actually the smallest resultant you can get among all of the conjugates, so change of variables, where f will be in, well, in PGL2, but actually f should just be az plus b, where a and b are rational. Well, a not zero, obviously, so you can conjugate. Okay, so basically, and this looks a little messy, all I'm basically doing is saying among all change of variables that looks like this, and I want it like this because I want infinity to stay at infinity for precisely the reason we're talking about points that are integral with respect to infinity. Among all these changes of variables, pick the one where the resultant's smallest, which, or at least one of them if there's more than one. Okay. Then we make a conjecture, which is the dynamical analog of a conjecture of Serge-Lang's for elliptic curves. Actually, Lang and Demyanenko, I guess. Which says that if phi is affine minimal, then the number of, I have to write it that way, the number of points, oh, also, of course, phi squared is not a polynomial. You want to be in the situation of the theorem. The number of integral points in the orbit is less than or equal to a constant that depends only on the degree of phi, not on the actual map. Okay. Okay. And actually, one of the project groups was looking at this sort of problem for certain families of maps, because there's sometimes when you can actually get, can do this. But in general, I think it would be very hard. In the general case, since the theorem that this is finite seems to depend on Roth's theorem, to actually get a uniform bound seems quite hard, in complete generality. And in the last 30 seconds, let me mention, this is one definition of affine minimal. Another possible definition, which is actually the one I think I put in the notes, is that instead that the height of phi, which is sort of just looking at the height of its coefficients, should be the minimum of all possible ways of changing coordinates, okay? And these aren't quite the same. but the conjecture should still be true with either definition. And there's certainly been some suggestion in the group that's working on this that neither of these is really the right definition. And in fact, that even restricting to affine minimal rational maps is cheating. And one should actually look at sort of, one should clear even more stuff away. Okay, so there's some interesting questions. In other words, what I'm trying to say is it's not clear that this is the right definition, and it's not clear this is the right conjecture. But at least these are more or less analogous to what's to the definition and the conjecture over elliptic curves. Thank you. Questions? Yeah. Yes, there is discriminant instead of the resultant, but I mean the discriminant is the resultant of a polynomial that's derivative. This to depend on the discriminant? I'm actually not sure whether or not I expect that, but the conjecture in elliptic curves is that if you look at a minimal equation, then the number of integer points should be bounded. It's not just a constant, but it's a constant. It does not depend on the discriminant. It's a constant that just depends on the rank of the curve. That's the conjecture. In this case, essentially the rank is 1 because we're looking at we're taking one generating point. So the analogous